Done.
Right.
Okay.
Hello, thank you. Good. Before I start, I would still like to extend once more as a part of the local organizing committee, very warm welcome and thank you for coming. Hope you all have an amazing time here the next this coming week. So yeah, thank you for giving me the chance to do this. Supernova Cosmology, a bit different from what we have been hearing in the last two tutorials. First thing first, so supernova type 1A, what does it, how is it made? It's made basically by, as is understood, from white dwarfs, accreting mass, reaching Chandrasekhar mass limit. And then so basically there's a thermal runaway, and within a few minutes or a few seconds that everything collapses and then it forms this huge light of supernova, so bright that it can outshine the entire host galaxy that it's coming from. Yeah. And so there's some speciality to this formation of supernova 1 from white dwarfs. We'll deal with that in a bit. You see this animation here from NASA, which shows this very clearly. I'll use this. So it's just for a better intuitive purpose. I would like to ask quickly, just so that you're all again back in the mood. What do you know what this Chandrasekhar mass limit is? Yes, please. Anyone wants to counter that? Yeah, that's it. What is the Chandrasekhar mass limit?
Yeah, we're not repeat the answers for the.
I will. 1.4 solar mass. And what would happen? Can you intuitively guess, if not already aware, if it had not reached that mass limit, like if it was under 1.4 solar mass?
You want to talk about that or?
I'm asking a question, maybe some random data I can ask. Just go for it. There. Yeah, if it doesn't. Oh, there's
a nova, if enough hydrogen builds up on the surface of the white dwarf, then reaches a sufficient temperature.
Yeah. So. So basically, if you don't reach, so it goes on to become this black dwarf. If it doesn't reach that trigger level. But anyways, it's so that's most of the astrophysics we'll do with supernova at the moment. Now we'll deal more with change gears and we'll go into how is it used for cosmology and as a dark energy probe. So let's see. So when we look at the night sky, we are basically before that we live in a universe which is broadly governed by the cosmological principle. I'm laughing a bit at the moment because just at the moment back at the break, Rob Knob sitting over there was telling me excited that we will start with the cosmological principle. So I asked him, how do you know? But yeah, so we live in a universe which is governed by the cosmological principle, and it's expected that it's a homogeneous, anisotropic universe in the large scales. So when we're looking at the night sky, broadly, we're interested in two things. We're measuring the flux, and we want to know the redshift. Now, the redshift, as you see, get this through. Yeah. So the redshift can be connected to the wavelength of the object that you're observing in the night sky from the point of its emission to the point of your receiving at the telescope on Earth. The other thing is the flux, which we're interested in. Basically, it's one way of saying the brightness distribution of the object that you're measuring in the telescope. Now, the flux is given by this formula, which is what you have all known and seen it from your high school, so you're pretty aware of that. The thing is, the beauty here is that if you were aware of the luminosity of the source that you are measuring, then you can, in principle, measure the flux of that object at different times, like just for intuitive purpose, let's say today, and then a few days after, and then a few days after. So you get different measures of your flux received. And because you know the luminosity, then you can take the ratio of flux. And then as a result of that, you can get directly an idea of the distances. So it's a relative distance you can get as a ratio of flux. This is very elegant, simple, but very strong, very powerful tool to have. So measuring fluxes at different cosmic times, you can get a scale distance estimate of the universe. The question is, this can be then any objects that you observe, and you can apply the principle that theory and get the distance. Why are we interested then specifically more so with supernova type 1a with this mechanism? You can think of some reasons. 1, 2, 3.
We should talk together for that.
Yes, please go ahead. I'll give you some time.
So I can sit down.
Okay. Anyone? Yes, answers.
Really bright.
Very bright. Anything else?
They're repeatable.
Repeat the rule.
Same every time, approximately.
Okay. Yes. I'll take one last answer if anyone has said.
That's pretty common.
You should not answer. Okay, I will. So, most of the answers that were given were correct. So the reasons say here. So, when corrected for some, here's some of the jargons that is specific to type 1 is from the smallest, which is stretch and color. When corrected for the stretch and color, and so stretch is in everyday term, you can think of it. If you think of the light curve, which is the distribution of the luminosity function of the time, the stretch in rough words is the width symmetrical on both sides of the peak brightness. So this and this side. I don't know if the people online can figure out what I'm saying. So that stretch, and then the color is if you take by theory the definition of color is the difference in magnitude of distribution measured between two filters, let's say UV or VR, etc. So when corrected for those stretch and color parameters, supernova type 1a light curves show remarkable homogeneity in the distribution. And so that makes them an amazing thing, what we call as a standard canvas. There's also the brightness thing, which someone mentioned in the they're very bright for us, so they can be seen and crest to a very large depth in the universe. And they're also very easy to distinguish compared to the other type of supernova categories. All this combined, it makes an amazing recipe for type 1 supernova to be used as distance rulers in the universe and as a standard candle. This light curve animation that you see over here. So someone mentioned on Zoom that they cannot see the pointer. So, but anyway, if you see this animation, it gives you a not probably
Your mouse.
Mouse pointer.
yes. So that gives you a sense of how different kind of light curve distributions, if corrected for those properties of stretch and color, can give you a unified standardized light curve, which then can be used for those purposes of distance estimates that you mentioned. That leads me to the trip equation, which is centered to cosmology analysis with supernova type 1 in modern times. We'll keep encountering this quite often in the upcoming slides frequently. So the trip equation, what it says over here, is that there's a distance modulus, the distance kind of self-explanatory. The distance modulus is given as on the right, you see a few terms, the apparent magnitude, the absolute magnitude. So in intuitive terms, if you were to think, you can measure the brightness of an object. Let's take this everyday example. You are standing on the road and you see a car in front of you and you see its headlights on. And then as you see the car moving away from you, you see the light getting dimmer and smaller. Your brain automatically, without knowing, maps out that fading of the light, and it gives you a sense of how far the car is gone from you, right? This is what it's the concept of the absolute magnitude and apparent magnitude fading. So the absolute magnitude is if the object of the supernova were placed 10 parsecs from you, the brightness distribution that it would have had, and the apparent magnitude is in terms of that, how farther or nearer to you is. And so you subtract those, in principle, you should be able to get the distance estimate of the object from us on the Earth. But that doesn't finish there. There's additional terms there as corrections to the distance estimate, which includes things like the stretch corrections, the color corrections, there's some additional host galaxy corrections, and there's a bias term correction. So I'll try to go through each of them in slide there. So first thing is the stretch and the color like we had encountered in the previous slide. These are intrinsic properties which you correct from on the supernova, and that improves your light persistence estimation. The gamma G host is a host galaxy correction which accounts for any additional residual relation between the supernova luminosity and the host galaxy properties. And then there is this delta mu bias. So the delta mu bias basically accounts for the fact that we'll come to that in more dedicated slides later, but at the moment, the delta mu bias, what basically says is that your supernova detection is using your instruments have a selection bias, meaning you preferentially select some and you don't select some rest of those. And so that is yes, because so if you're asking for the apparent absolute magnitude, can I go back to the question?
Yeah, I think should be a negative sign.
No, you mean here. So the M naught is actually not the absolute magnitude, it is absolute magnitude standardized. So there are some additional terms involved there, and that's why you can imagine in your mind something like this. And plus some terms. So it's standardized term. So we'll come to that also in a bit. So that's why it's a plus n.
Okay.
And what I was talking about the delta mu bias. So delta mu bias accounts for that selection effects inefficiency, meaning that you choose some, you don't choose some when you're through your telescope. Ideally, the brighter ones gets detected. So that can technically bias your sample and then hence the rest of the science that you do with it. That delta mu bias tries to take that into effect and corrects it. Like I mentioned below here, the trick equation is an empirical formula, meaning it's been developed through the data that we see over the years. That brings me to some quiz. So light for feeding, the one that you see on the right is the raw data, and then on the raw data, the fits in different parts and filters, like in the different color cards that you see. I want to ask the audience, can you tell me this light curve fitting, what's the purpose? Are they only to make them look good, or is there some additional info to it? I'll give a hint, and the hint is right there, staring at the face. The second question, which terms standardizes the business modulus in the trick equation? 1 minute.
And brown color,
This is a small version of the question, it doesn't contain the question asked. You can think this is standardized by brightness. But still, the question is the same.
Just the algorithm.
Okay. Maybe I'll look to this side. Someone from there, you know, imagine. I see Chris. Yes, right.
Can you repeat the answers for Zoom? Yeah.
Yeah, so someone mentioned it's for alpha and beta. Anyone else wants to add anything or? I think you are very interested.
So these supernovas are standardized a bit, and so the goal is to get all of these curves to line on top of each other. And then once you do that, they already all have the same effective brightness, so that if you normalize those to the distance, ladder that we have, then you use them as a standard.
If, shall I repeat what Chris said also? So here's the answer, and you get it perfectly. So the light curves fitting is done. I mean, it's like any regression fit that you have done from high school. So when you fit to a curve, you get some parameter of fit output from the goal here is exactly that, to get those fit parameters, and the fit parameters are those going into the equation, which then makes the distance of the brightness distribution standardized. The fit terms, the fitting parameters that come out of the light curve is the goal. So light curve fitting itself is not the standardization per se, but to get the parameters and then fit it in that equation is what makes it a standardization. So to come to the question's answer, get the parameters needed to standardize the brightness, stretch, color. So light curve fit is not standardization itself, as I mentioned. And this software here is the parameter of the equation, which is standardizing output x1 minus beta c, stretch and color. Let's see what next slide is. Okay, so the same slide, but now just elaborate a bit. So those parameters, like mentioned by the x0, x1, c are the fit parameters that you get from the light curve fitting. The corresponding names. So from here you get the amplitude, the stretch, and the color. I would like to give a disclaimer. You should not confuse C with the speed of light. It's we mentioned color as C. And the most popular light curve fitting at the moment in the community is SOLT, which stands for Spectral Adaptive Light Curve Template. And SOLT 2 and SOLT 3 is currently popular. So yes. I have a few more quiz questions. So do you remember in the first slide I said that we live in a homogeneous and isotropic universe, and where? So I think if I don't remember if I mention again. So our distances that we measure in the universe are proportional to the scale factor A. And that scale factor parameter A divided by A dot. Do you know what physical quantity that parameter is? Can you remember the name?
Altogether, Hubble.
Okay, there's unanimous answer to that. There's no confusion about that. Given then, okay, then I come to this. So don't imagine this is so this is the distance estimate expression of the luminosity distance. DL is the luminosity. If we have this expression, I would like to ask you for low redshift, that is Z less than 0.1, that is very small, can you derive the luminosity distance expression from the above and say what is its significance? It looks big and complicated, but if you see through it, you can do it without a pen and paper. And you and also has some students. And I give an intro there, make an assumption about atoms at your C.
So it can be.
Wow, it thinks I'm speaking in person.
Cancel.
Yeah.
Trying to get my, yeah, when it goes there, the mouse disappears.
It's the other most, oh, yeah.
Oh. Okay, anyone? I'm not looking at you. Anyone, maybe from that side this time? Yes.
And then a further confirmation where no zero. E already is not.
Yeah. So. The assumption that you made is this becomes a small when redshift tends to 0. I don't know if it's visible from there. Yeah.
Yeah. Go ahead.
Well,
So why did it fix
maybe there.
No.
No?
Yep.
When the 0, and so your D the difference of D over H naught. Remember, E of Z then becomes 1, so you integral of dz. Which are C for that's your.
Yeah, I think we will. You have a question about the same.
You can the remote.
I think you should go ahead because
Yeah,
we'll
okay.
talk your way through it.
Yeah, so, oh, sorry, there's a second part to it, right? Can you say what is the significance? Yes. Okay, can you repeat it? So, oh, the answer, no model assumption, someone said. Anything else? It's pretty simple, you know it. Yeah. So, where's the mouse gone? Why doesn't it move? Okay. So lower exit, it's basically the linear Hubble visiting. So that means it is a region where your distance and the redshift is linear in relation. It has a special significance of its own in the sense that it is this region that gives the precise calibration of Hubble naught, Hubble parameter H naught. And it gives you foundation of the cosmic distance ladder. Basically, you can think of it as the first rung of your distance scale, based on which you can then measure the further upper distant universe. Anyway, we'll not go much in H naught analysis here. Let's come back to redshift. So the CFA for me already gave, I think, a bit of introduction about those. But redshift in everyday terms for us is basically we were aware of the Doppler effect, but this is, let's imagine, Doppler effect in light curves or light waves. It can be related to, like I mentioned, the wavelength angle, the wavelength absorb. And rearrange this term 1 plus redshift is quite important in our sense because it kind of accounts for the line of sight as the photons traverse the universe. You will often encounter this factor in added to account for this redshift, to calculate the redshift. Redshift can be measured in two ways. I think most of you are aware of that, spectroscopically and photometrically. In an ideal world, you would want everything to be measured spectroscopically. But that comes at a cost. The cost is more telescope time, and especially in the modern era, in the days of LSST, it's not possible to have the luxury of observing everything spectroscopically because of the sheer amount of objects that you'll be observing. So what you do, you fall back on photometric redshift, and the photometric redshift, the price you pay is that although it's easier and it's quick, so you can get more number of objects with photo Z, but the price you pay is the inaccuracy. So the delta of Z is incomparable to the spaceship, which is almost null. So then the next question is, like I mentioned, the LSST will observe tens of thousands of supernovae. Most of these will have only photometric redshift available. Right? What advantage then you think does? Oh wow! What advantage do you think that supernova cosmology have over other probes in terms of photometric redshift? 1 minute or two. Hey, time out. Someone who has done the maybe from this here, this cluster here. Rob stays on the table next to it.
They're really standard objects, so can I make it easier to like your template fit to get your photometric redshifts?
Can you repeat the full answer?
So the type 1A supernova could be a very like standardizable process, meaning that it's like you kind of know what's light to expect with different wavelengths. And so if you're suddenly getting light, a lot of light coming in at different wavelengths, you know how much redshift that's in there.
In spirit, I think yes.
You should repeat the answer for Zoom, they can't hear us.
Yeah, that was a big answer. I think he meant that the redshift of the. Did you mention the galaxies?
No.
No.
Didn't mention the galaxy. No.
Can you please repeat?
So
You're talking about the supernova only.
Yeah, I kind of lost track.
supernova light curves, if the type 1A supernova light curve is just a very standard like template thing that happens all across the universe. If it happens over here, it's the same thing as if it happens way across the universe over there. And so if something looks different, coming from a different spot of the universe, you know that all of that difference is coming from the redshift of the thing that you know about. So it's easy to do a template fits on your photometric bands to get the redshift.
Okay, so basically what you're saying that if you get the template fits, then you can just anywhere supernova else here there you can just scale that like the shift, and then you can just get the redshift anywhere.
Hopefully.
Yeah. Welcome to the someone behind it, please.
Possibly we have better photometric redshifts for low receiving Earth.
Better photometric redshift for losers. Yes, Chris.
So typically, you're actually getting the redshift from the host galaxy, and you can go back and get that later. So I'm not sure exactly what you're asking, but maybe the point you're making is that it's a finite number, so it's easier to get spectral follow-up on these rather than like large scale structure where there's no way we're ever gonna be able to measure all of these spectrosity.
Yeah. Anything, any last ones of someone there?
You have the light curve, so you have four dimension in terms of data for one of the compared to for galaxies you have the same number.
I didn't get that. So you have the light curve. Can you please repeat?
Yeah, so the light curve gives you higher dimensionality in terms of data space, compared to the supposed galaxy, or just any galaxy proposed.
Right. So the added advantage of the light curve, which will give you the additional high dimensionality in terms of redshift. Yeah, Amanda, I think raised.
I was gonna say something similar, like breaking degeneracy.
Yeah. Okay. Yeah, thank you. So I think most of them are in line to what I was expecting. The most closest I also was like what Chris said. Basically, very easy. You have now option of two redshifts in addition. So you have the host galaxy availability, you have the supernova itself, right? Like Chris said, you can always miss the transient itself, but you can come back and get the host galaxy redshift from the but overall, what it does, having the possibility from two, is that you with a greater confidence rule out the possibility of a catastrophic redshift error because you have two options, let's say, two for one. Yeah, so that is a very supernova specific advantage that you will get.
Can I ask you a follow-up question?
Yes, please.
So if you were to use the light curve to also measure the redshift, isn't that an issue because you're gonna use that velocity when you're actually measuring W indication?
There's degeneracy.
Is the degeneracy problem, and it wouldn't be better to, since that's the thing you're using for the cosmology, it would be better to not use that for the host redshift? Or is that?
And you can defer that if you're gonna get to that later in the lesson.
It's yeah, I mean there's an elaborate answer I would like to give. Maybe we can discuss this a bit later. Yeah, it's something we deal with. So coming back to the imagine the trippy question once again back in your head, and so we were trying to account for the biases and correct the distance and the brightness distribution, right? Apparent brightness. Now, the factors that you saw were vital inside that trippy question might be stretch and the color parameters. It is something of very high interest in the research community of studying the relations between redshift and color redshift and how does that affect and how does that bias the relationships. So there's these two factors, the stretch and the color. As you see, the stretch is not correlated with the color per se, but there's when you see the when you study the relationship between color and redshift, you see there's a strong anti-correlation between the color and the redshift, right? And this has a lot of significance or consequence, as you'll see in the coming slides. Again, this question I'd like to follow up on that is like, do you happen to know or can you guess why is there a strong correlation between redshift and color? 1 minute, please.
Are you asking a correlation between redshift and color, or a correlation between photometric redshift error and color?
That's a good question, actually.
Come on.
Yes, in general, redshift and color. But we'll come to that photometric redshift error and the color error also, I mean the color relation also.
Over here,
That one. Yeah.
That's right.
Okay. This race is so anyone? Anyone wants to go first? I see some faces smiling.
Redshift thinks it's rare.
That's pretty, it's a very self, once you hear the answer, when I heard, figured it out, I felt very dumb. Right, this is the answer. There's this, because Redshift does make it, so if you are aware of the, let's say, as you go to a higher Redshift, it becomes redder. So there's a strong degeneracy between Redshift and color. Yeah. So what Rob said is right. Now, if we come more deep, we focus more on the photometric redshift, the question that was raised by Rob before. So now if we focus more on the photometric redshift, we see some strange interplay going on here. So for example, when we are doing the light curve fit, now using photometric redshift, we find that there is a strong anti-correlation between the color and the photo Z, right? So that means the bigger is your photo Z error, the redder is your measured red color, so bigger in value. Now, what the consequence of that is that this change in color kind of self-corrects for the error in your photo Z that trickles down into your distance estimation. So to account for the fitted photo Z uncertainty, one would then, if you were not aware of this color interplay happening, if you are just told that we're fitting with an additional photo Z parameter in your distance, which goes into your distance estimation, then you think because the photo Z has an uncertainty, you would naively add like a sigma of P or Z, Z4 times the determinant of Z, just to account for that uncertainty. But we don't do that explicitly just because one of the reasons is this, because the color kind of automatically negates internally due to its anti-correlation of that. So then this has been shown over few analyses like Mitra, Tesla, Rebecca Chen's paper recently. So then I would like to ask, like, how is then photo Z error propagated with distance uncertainty if we don't explicitly add this term to the measurement of your uncertainty estimates? One minute. What's that? Oh. Okay. Anyone? Any guess? No one? Yeah, yes, I raised.
If you like having a smaller scene spectroscopic sample, like that would maybe these analytical variants, we use like sample of this.
Can you repeat the spectroscopic part?
So because, as you mentioned, like spectroscopic redshifts are like, you can trust them to be true. So I can, use like a spectroscopic sample to understand the color redshift relationship. You'll have some dispersion, but then I can like maybe sample from that space and then build it. Basically,
To map from there and then inject it back here.
Right.
Okay, one answer. I saw you raising my hands.
Yeah, we're just, first of all, commenting that it doesn't need to be an anti-correlation, right? Because that's the definition of color, right? Like which color difference you're taking,
Okay.
correlated. And the answer basically that one has to do the proper propagation of errors, taking into account the correlation, right? And that will then subtract that term.
Yeah, that's about pretty much the answer. So, overall, there's the error propagates or trickles down to all the parameters, different parameters here. So, like I mentioned over here, so fitted unsolved to fitted uncertainties on the other parameters resulting in increased distance uncertainties overall. One being like an example of the sigma of C, just to show you if it is the true redshift versus the photogenesis as you go to the higher redshift, the photogenesis impact on the uncertainty of the color is stark, as you can see. So that's how it trickles down. We come to the next big part, or I hope I have time. So this is the bias correction. So in an ideal world, like I mentioned, and I mentioned there, in an ideal world, you just observe your supernova, and then you subtract it and from your scale of or your benchmark distance, and then basically you get the difference, which is equivalent to the distances, as an estimate of the supernova is. And also your telescopes in an ideal world would be able to observe all this. It points to a direction in the sky, and it observes all of those candidates. But that's not how it works in the real world. The difference is, like I mentioned here, our telescopes are they don't record all that supernova or any other objects. Basically, we miss systematically the fainter ones, and so there are different things that we miss out on. This includes the fainter supernova. Then there's the line of sight dust that affects the scattering happening. And all this combined, what it means that our measurements contain a small systematic biases. And so this biases, again, propagates through and biases our analysis and the cosmology and the accuracy estimation that we do down the line. The naive Hubble diagram, for example, if you were to just fit the light curve, get the parameters, and then put it back in the distance formula, and get your distances, and then you construct a Hubble diagram. What's the Hubble diagram? Like I mentioned below, the support of the distance versus redshift. You do that. It doesn't account for all the selection biases, and so in a way it's flawed. So you need to fix that. So how do you fix that? So you fix using the BBC method, which is the one that is mostly in vogue at the moment. So BBC stands for beam with bias correction. And so the BBC method analyzes the salt two or so three fitted parameters like the redshift, color, stretch, and uses a large simulation parallel to that to determine these biases, and it corrects that. Remember the delta mu bias term in the triple question, and it produces a bias to the Hubble diagram. Let's go to the next slide. I have a quick question for this. So imagine this board, and someone is an archer and throwing arrows, and you see these two patterns like the arrows on the board. The question is, do you think more arrows, which you can map to like more data, will help hit the bullseye, which is the center of the yellow, which is the true value? If yes, in which case will more arrow help to hit the bullseye here, there, or both the cases? 1 minute.
30 seconds.
30 seconds, yes. Okay, I think it's pretty easy. That day, I wanted to ask that day.
Oh, yeah, we were discussing on whether like the nature of the vibe on the right one, like it's very concentrated, there's going to be there, so have to be high or we ripped it, it might just have been high.
Which one was that?
On the right, and then on
This
the
one.
left one, it's a very scattered plot, you probably have a chance of hitting this at.
Right, anyone wants to counter that?
We agree.
Okay, so yeah, so basically, that's what he said, so more data here kind of washes out the errors and it averages out, and so that is what is basically you can think of as a statistical error. But here on the right, you see, no matter how much you go on increasing your errors, it will be systematically there, clustering there. And so more data doesn't help, it just makes us more confident in the wrong answer, so that's a systematic error. And so in the current era of precision surveys, our biggest challenge is finding the systematic biases. In supernova cosmology, where does this biases come from? The most common one is the selection bias. For example, you must have heard the Manquist bias, which is basically at a high redshift. You again preferentially select the brighter supernova your sample is biased towards the brighter ones. Also, if you were doing photometric redshift cosmology, then the redshift axis of the Hubble diagram will have more uncertainties. Also, that will affect your distance estimations. So you can see this as what happens in this upper magnitude versus redshift plot. But if you were only selecting the red ones, which is like the classical case of the magnitude class, your derived or inferred cosmology from there will be biased compared to what was originally meant to be, and that's the deviation that happens, the selection biases. So again, revisiting the trip equation, this is exactly where the bias selection comes into effect and it accounts for. So what it does is it takes that trip equation and then it does a high stat bias sort sample rather than it, and then it finds the true, and then you subtract that, and then you get to the bias you plug back in. It is done in this multi-dimensional space. It can be few to higher dimension. There could be like EDC 0, 1, 2, 3, 4, 5. Either like something like redshift, star, alpha, and beta. Question: what redshift in the new true redshift that C that we use? Do you think it's true redshift or photo Z? Assuming you were doing a photo Z cosmology.
You mean in a simulated sample?
Yeah, so you see this here. So you're finding the truth so that the subtraction gives you the bias, right? Now, while finding the truth from this equation, you need to fit some redshift, right? What redshift will you use? The true redshift or the photometric? What are we? 1 minute, please.
Sampling around. Yeah. It's trying to figure out what the bias is. On one hand, you want to do it. There are my people.
Yeah. It's minus the view rather according to whatever. And you plug in okay, this is more like a question, like a more of a moral question. You can, so anyone wants to answer? Yes, please.
You spoke.
You spoke.
You gotta use the true redshift in your simulation to figure out your selection function, but you're gonna photos. You can take those.
Yeah, but okay, anyone else? No. Oh, there's a hand. Yes, please.
We think we should use the photo Z. Because when you're doing the simulated samples and sort of figuring out how to do the bias correction. You want to use the photo Z then, because when you're looking at actual data, you only have the photo Z, you don't have the 2D. So you want to set up the bias correction to be able to have photo Z in the input.
That's an amazing answer. I should give him some chocolates after that. So he said that you should use the photo Z because in the real data, you only have the photo Z. And so you want to mimic as close to the real data. So you should simulate on the photo Z and then find the bias correction. Actually, that's the answer because, like I said, it is a moral question. You can, in principle, do the true Z as well. But then this is all built with the vision of the real data and preparation for the real data. So there should be, so we do with the photo Z in the simulation as well.
Can I ask a question?
Sorry?
Can I ask a question?
Yes, please.
How do you know that the way you make mistakes in your photo Z's on the simulations are the same as the way you make mistakes in real data?
That's an open-ended question because the photo Z modeling is a topic of research itself, and so of course you will not that's a downside of using photo Z. You don't know exactly how the real data are modeling. So there's no clear answer to that. It's the best guess that good figures, etc. Yeah.
Can I just add? Just add that I think we're busy as we can simulate galaxies photography now with supernova, precisely so we can run the galaxy photography through all the single algorithms. So we get what we folks think is we get for these galaxies that was supernova.
Yeah. We're slowly moving towards the Hubble diagram. Now, so this is a Hubble diagram. One of them is bias corrected, one of them is not bias. So what is there? So this is the distance, this is the redshift for the bottom panel is delta mu, which is a Hubble diagram, so the distance modulus residual. I'm asking, can you identify the seeing these two plots side by side, which is a bias corrected Hubble diagram? Maybe 30 seconds.
Cosmology is better, but it's also better.
That's mostly because
There's some residual.
Okay. Answer time. Do you want to answer?
Sure.
Yes.
The one on the right is the one that's bias corrected.
That's first.
Sorry. The one on the right hand side is the one that is bias corrected.
And why is that?
Because of reduced scatter, but more importantly, it's much better center around the dealer pole.
Exactly. So you see the scatter is less. And so that's a direct visual proof that once you do the bias person, like your distance estimation is less scattered, this dispersion is reduced now. Between blue and red samples of supernova, right? What do you expect to be needs more bias corrections? Also, maybe 15 seconds or 30 seconds. So the more bluer supernova, more redder supernova. Yeah, that's one.
That's not.
Okay, someone wants to answer that? Yeah, and can you answer why it's in red? Right, so it's also pretty self-explanatory, I think. So he said it's the redder sample of supernova that is expected to need more bias corrections because of the high redshift. That's, like I said, it's more redder, and so this is again a flaw that we're showing that the new bias has two sub samples. One is redder and one is bluer supernova. And as you see that as you go to high redshift, the bias in the redder sample is more exaggerated, but I'm not sure about that. So I'll finish with few 4 or 5 slides, I think. So this is the last part. So the bias correction is one part that takes into account. There's another part which, if you do photometric supernova and cosmology analysis, which is your sample can be contaminated with non-1A because of misclassification, which thinks is 1A, but it's not 1A, or it's core collapses, etc. And that part is being addressed or taken care of by what is called the beams. And so beams with bias correction together from the DEC. So what it does is, apart from the selection biases, like I mentioned before, so you can do a hard cut on your sample and say, this is the one I'm completely confident about, as one is, and I'll keep them and I'll throw out the rest one. But then you fall back to what becomes like a gold sample. It's a very small, accurate sample. So you don't want to throw them. You want to keep the other samples as well, but you have to know and account for those, and that's what beams does exactly. So we must statistically account for their presence. So what it does, it takes the likelihoods of a given object being 1A or core collapse and combines and kind of gives you a mean posterior estimate of the distance of those factors combined. So this is what you see then final bias BBC corrected beams with bias corrected Hubble diagram looks like. So you have the blue ones, like the more well understood supernova, and then you have the redder ones there, which you see on the color bar on the side with the higher probability of them being the chance of them being a core collapse. And so that's a bias corrected complete Hubble diagram. I have a quiz question to follow up with this. Why do you think the red ones, which are supposed to have a higher chance of being a core collapse, you see systematically on the upper part of the plot and not scattered all over? 1 minute.
Yeah, maybe if there was like, then we could that.
Okay, so let's ask the audience. Do you have an idea? Answer. Let's see if someone else will.
Maybe go ahead and give the answer because we're.
Okay, I think he has an
If
answer.
we're running out of time.
You can go.
Maybe it's because of the composition of the supernova. and then, Chris was talking about how,
So maybe you can only tell the difference between them if you can measure the spectrum of that. Which is when they're brighter, when they get quite dim, then you're more likely to see some.
It is. So, core collapses are generally dimmer than the ones. And so you see the higher on the y-axis is the more dimmer side. So you see the systematic is there because it's the dimmer there. Yeah, just the easy answer is that there are more complexity to it. So in the concluding slide, I would like to mention that we have seen the recent 5 years dark energy survey DES results, which is successfully exhibited that they used photometrically classified supernova all the while still using spectroscopic redshift to do cosmology and prove that it's more than feasible to do that cosmology successfully in supernova. What they haven't done was still use additionally photometric redshift. We are at the moment working on that, and so we're preparing to do a full photometric supernova as an effort of that. We have recently released a paper which is in undergoing review, and we still have seen from the previous Hubble residual plot there is a slight bias, so we're examining those biases. And although small, they're not really burning questions, but we still need to understand them better and account for them. And going forward, I think that's the way for the LSST. If I have a minute, I would like to finish with a little historical video. Like by the time we anticipate the Hubble diagram of LSST first year data to be produced, we expected like 2030 if things go right. It will be exactly like 100 years since when Edwin Hubble in 1929 produced the first Hubble diagram with 22 intergalactic nebulae. And if one were to say back 100 years back that in 100 years you will have hundreds of thousands of supernova and you will have an understanding with sub-person level of the dark energy and the accelerating universe, would have taken it. It's amazing. So we're holding our breath for the next decade to see this golden age of astronomy. And I've compiled a few Hubble diagrams to see all the way from 1929 to date and what we expect in the coming days. That's this, we don't know what.
Thank you.
That's it.
Thank you very much. So we can stop the